In this video, we'll see how artificial intelligence can be used to improve quasi-dynamic simulation speeds in the Texas grid example. Study case 9 should be activated. The artificial intelligence approach consists of training a neural network to approximate load flow calculations for a given electrical network topology, after which the neural network can provide a very fast and good assessment of the network state for different operational conditions. Before looking at the commands in PowerFactory, let's first understand the concept at a high level. A neural network is able to learn how to carry out tasks without being given any instructions by being trained on a large dataset of inputs and outputs and analyzing how the inputs affect the outputs. The inputs consist of, for example, active power of generators and loads, and the outputs will be calculated quantities such as the resulting line loadings. In PowerFactory, this means first creating a dataset of many different samples, utilizing PowerFactory's probabilistic analysis function, which uses distributions for the inputs. Once the dataset of inputs and outputs is created, the neural network can be trained on the dataset. When the neural network has been trained, it can then be used for a quasi-dynamic simulation where the fast performance times allow a great many time steps to be analyzed quickly. To use the neural network functionality, the PyTorch library first needs to be downloaded and the path configured within PowerFactory. This process is described in the Advanced Installation and Configuration Manual. The neural network commands are located in the Additional Tools toolbox. There's one command for the setup of the neural network and one for the dataset generation and neural network training. Let's first look at the Setup for Neural Networks command. Here, there's a link to the related neural network training command. We'll look at this later. The neural network will be used with a quasi-dynamic simulation, so the load flow settings and output variables are taken from this quasi-dynamic simulation command. A neural network is trained using a training dataset for which distributions are required as inputs. These can simply be defined by the user. But this command makes it possible to automatically generate the distributions from existing time characteristics. When the command is executed, the parameter distributions are created together with estimated correlations. The command has already been executed in this project, so the distributions and correlations have been created. In this example, we want to focus on possible load variations in the south grid. So, an additional discrete distribution has been created. This distribution is linked to the load scaling factor for all loads in the south grid, so that the underlying value of 1 is varied between 0.8 and 1.4 during the neural network training. In summary, when training the neural network, the distributions estimated from characteristics cover the typical power generation and consumption throughout the grid during the period of the quasi-dynamic simulation. The additional discrete distribution enables the exploration of potential load variations in the south grid. Now, let's open the neural network training command. This can be used for both dataset generation and neural network training. Here, the method New is selected. With the Continue method, an existing dataset is extended or the training of a neural network is continued. On the data generation page, there's a link to the probabilistic analysis command that's been used. Distribution correlations are considered in order to model dependencies of loads and generators on each other. The input variables are automatically selected based on the defined distributions. For the output variables, the transformer and line loadings have been selected using a filter to limit the results to those of the south grid. On the neural network training page, the number of training epochs is specified. The command could now be executed. However, as the data generation and training process is computationally intensive and takes some time, this application example comes complete with a pre-trained neural network. The location of the neural network is defined in the study case. This plot shows the decreasing training error over epochs. If the outcome is not satisfactory, the continue function in the neural network training command can be used to expand the dataset or train additional epochs. This button can be used to verify that the current network topology is the same as that on which the neural network was trained. Now, the neural network can be used in a quasi-dynamic simulation to analyze different load flow situations. For this purpose, an operation scenario has been created to model an increase in load in some parts of the grid and a decrease in other parts. Let's first return to the neural network object and use the Check Consistency button to check that the network topology in this scenario is the same as the topology in the scenario used to train the neural network. We can see in the output window that the topology of the system is consistent with that on which the neural network was trained. The Quasi-Dynamic Simulation toolbox is now selected and the command is found here. The analysis will be carried out for a complete year using a 1-hour time step. On the neural network page, the neural network is already selected. The command is executed. The calculation is complete, and these plots can be used to examine the results for two lines of interest. We can see that for this line, the loading for this period of time is quite high. To validate the quality of this neural network approach, we'll run a quasi-dynamic simulation with a standard load flow just for this period. The results will be stored in a separate results file. The comparison in the plots shows us that the neural network calculation is in fact a good approximation to the results obtained using the standard load flow method. And the calculation is completed in a fraction of the time.